Hey everybody, day 400 of practicing isolation and social distancing. I think we're all doing pretty good. So for this video, what we're going to do is we're going to calculate the wavelength of a transition of an electron from n equals 2 to n equals 4. So if we go back to the Bohr model atom, you'll see that to go from n equals 2, you have to give it energy to n equals 4, right? So to go from n equals 2 to n equals 4, we're going to have to be giving it energy. So let's find what wavelength that is, and let's actually find what region that wavelength would have to be in. So like everything else, wavelength is going to be in meters, and n final is the last transition, which is 4, and n initial is 2. So these are actually the energy levels that we have. And RH is the Rydberg Constant. And this is negative 1.087 times 10 to the 7 per meter, right? And that does make sense because if our units are we're solving for our in 1 over wavelength, we should have 1 over a meter on the right hand side. So how would we solve this? All we would have to do is plug in our numbers. So we're going to have 1 over wavelength is going to equal negative 1.087 times 10 to the 7 per meter. And our final energy level is n equals 4. So it's going to be 1 over 4 squared, right? Minus, and our initial energy level is n equals 2. So it's going to be 1 over 2 squared. So it's going to be negative 1.087 times 10 to the negative, or 10 to the 7 per meter, 1 over 16 minus 1 over 4. So I've seen a lot of times people type this in their calculator incorrectly. 1 over 16 is a decimal number. It's a small number. 1 over 4 is 0.25. So we're actually going to end up getting a negative number here. So we're going to get the negative number, negative 0.1875. And our Rydberg stays the same. Okay. So our negatives are going to end up canceling out logically, right? Our negatives are going to end up canceling out. And once we multiply these two, we get 1 over wavelength is equal to 2038.125 per meter. So I get people that give me this as the answer, and that is absolutely not correct. We need to solve for lambda. So how do we get lambda on the top? Well, you take this number, divide by 1, right? So 1 over that. If you visualize it, you'd multiply both sides by lambda, and then you have to divide by 2038.125, right? So 1 over 2038.125 is actually equal to, let me pull that up, it's actually equal to 4.91 times 10 to the negative 7 meters. And that sounds right. That sounds good. So let's see what region that is. If you look at your electromagnetic radiation spectra on slide 4, you can actually predict which region that's in, and it looks like it's going to be in the UV range. So I could very well on the exam give you an electronic transition, and then I could very well ask you what range it would be in. So key things to remember in this problem: the Rydberg constant, your wavelengths you're going to be solving are going to be in meters. and final squared and initial squared. So make sure that you square them. You may get a negative number, you may not. And then once you solve for it, you're going to get a number that is not equal to your wavelength, but is equal to the inverse of your wavelength. So you have to do 1 divided by that in order to get your actual wavelength. So, and then if you consult slide 4, you can find out what UV range that's in. So if we had an electron that transferred from n equals 2 to n equals 4, the wavelength of this transition, in order to get it to transfer from here to here, we're going to need, what was it, 4.91 times 10 to the negative 7 meters in order to get an electron to transfer from here to here. So I brought this sheet back up so that I could show you how this actually applies to what we've already gone over. So I hope this helps. Stay isolated.